In this video, I will try to document why I like Jupyter and why I think it's advantageous to use this for homework problems. And so pretty much to show its strength and what we can do with Jupyter. This is not meant as an instruction video to teach you how to use it, but simply to explain why I like to use it. So some of the features that are used to just show the advantages or the strength of using Jupyter. And as we go through this semester, we will learn how to apply it. So I have a Jupyter file uploaded here, and I'm going to make a markdown here. I'm going to say, imagine this is like a homework problem. Problem 1. An object is moving at an average velocity of, I'm going to have a number, I'm going to put that as a mathematical expression, meters per second. Okay. It travels a total displacement, or distance, we can call that for now, a total displacement of say 20 kilometers. Okay. How long time did it take the object to travel this distance? All right. So if you don't know the equations, we haven't learned anything about it. You could probably figure that one already. But we're going to have an answer. So this is the problem. I'm going to put a Shift Enter, execute it. So it's the problem. I'm going to make a new markdown, and I'm going to call this here my solution. Okay. So the solution to this problem here is to say from kinematics we have the following relationship between average velocity, displacement, and elapsed time. And now I'm gonna put an equation on its own line that says that the average velocity is equal to the ratio or the fraction of our displacement. I'm going to write this as delta x, or the change in x, over the elapsed time, or the change in time. Let's see how that looks like. Okay, looks good. I want an extra space between that. Solving for the elapsed time. I can copy paste that equation if I wanted to, but I can also just say the elapsed time, delta t. It's going to be an equation. It's equal to the fraction of the displacement, which is delta x, divided by the average velocity. See how it looks like. Looks good. Go over the same box. Substituting in numerical values. I'm just gonna copy paste right here. We got our displacement was 20 kilometers, so that's 20,000 meters. I'm gonna keep this in same units. Drive at 50 meters per second. If I plug that into a calculator, I'm gonna get 667 seconds. See how that works. Oh, the S came down there, so I'm gonna keep my S in here. Okay, so 667 seconds is the answer for that. You say it looks nice with the equations and so forth, and it's relatively easy to type it out with some explanations. So we get the hang of this here, it won't take long to actually type out these problems and solutions. Let's take one that's a little bit more difficult. You can say, hey, I could do this in Microsoft Word as well. You absolutely can. I still think typing the equations, when you get used to it in Jupyter, is going to be a lot faster than using the equation editor in Microsoft Word. Take another problem here. So this is going to be problem 2. Ooh. Let's make a markdown box. So problem 2. Okay. So problem 2, I have that listed over here. And object is located at, so it has initial position at located at x equals 0 meters, and has an initial velocity of, what did it say? Same numbers here, 50 meters per second. So no, sorry, not the same numbers. 50 meters per second at t equals 0 seconds. Okay, so at t equals 0 seconds, the object is located at x equals 0 meters and has initial velocity of 50 meters per second. Okay, it maintains a constant acceleration of 0.5 meters per second. That's squared. So I'm gonna have to have squared in there as an equation, otherwise I cannot put it as that's just one way to use LaTeX to make superscripts. If I put an underline underscore instead of the caret, it will be a subscript. So it's a quick way to make subscripts and superscripts. So it has a constant acceleration as it travels to a new position, x equals 50 meters. All right. How long? The question is then, how long time did it take to travel this distance? That's the problem. See how it looks like here. Okay, I think it looks good. That square is sitting in a little bit odd place. Oh, that's because I have meters. Let's see, I got a meters per second. Oh, it's just because of the size of my window. But here's the meters per second squared. You can see how 2 is a superscript. Okay, how long time did it take? New markdown box, and do solution. Let's say from kinematics and having from kinematics with a constant acceleration. Again, I don't necessarily want you to pay attention to the equations or anything like this. It's something we'll cover and get started. From kinematics with a constant acceleration, we have, and what do we have? We have an equation that says x equals any new position is equal to the original position plus a term that involves our initial velocity times the elapsed time plus 1/2, gotta write that as a fraction, times the constant acceleration times the time squared. Okay, let's see how that looks like. So this is our equation from kinematics. This is one you might recognize from high school. We'll definitely also show how we get there. Okay, so we know everything in here except the time. So you may recognize that this is a quadratic equation, and we can solve it using the quadratic equation solver. You may recognize that is, what is that? B squared plus minus this, no, minus b plus minus square root of b squared minus 4ac divided by 2a, right? I'm just going to write that one right here. So t is going to be equal to, that's what you remember this, time. So it's going to be a fraction. And what did I say? Minus b plus minus, that is backslash pm. And then it's a square root. And then it's b squared minus 4ac divided by 2a. Let's see how that looks like. Okay, so that's the equation to solve for that here. And then we have to identify what is b, what is a, what is c. And we have those identified, we can plug that into the equation and we have a solution. It takes a little bit of time. You can do that on a piece of paper, not a problem. We most likely to make some small mistakes here and there on the calculator, forgetting a sign and so forth. But it can be done. I do not want to do that right here. I want to show you a different option instead. So let's go back up here and just state we can identify the values of a, b, and c and plug them in to solve for t. Okay. However, we will show the strengths of Jupyter here to solve it for us. Okay. So this is something called Symbolic Python. This is, I'm gonna make do you guys remember how to make it bold? Symbolic Python. And again, you will not be required to do this here any given time throughout the class or throughout the semester, but I want to show you how you can use it, and it's great to use it for even more complicated problems. All right, so Symbolic Python is actually a computer programming. So I'm gonna now switch this one into a code box, which it already is. So for code, they say we're gonna import. So in Python, you can make a comment by using the hashtag. So I'm gonna import Symbolic Python into our Python script. So keep in mind, this little cell here is now going to be our Python script, not scripts, just script. And Python is just a compiler. It can do only very few things, very basic things. So sometimes we have to import things so Python knows what they are. One of those is Symbolic Python. So I will do import, what's it called? SymPy, that's short for Symbolic Python, as simply as sim. Okay. And I can talk to you more about this later on, how we do this, but why we're doing this here. But don't be so concerned about the syntax now. I just want to show you the strength of it. Okay. Then I'm going to define our constants. We have our initial position is equal to 0 meters. We have our final position, I'm just going to call it x, is 50 meters. We have our initial velocity, I'm going to call it v0, that is 50 meters per second. And then we have a constant acceleration that is 0.5 meters per second squared. So those are our constants, okay? Now I'm going to define the variable we want to solve for. Define variable, and that is t. I'm going to create that so that Python knows that this is a symbolic value. So t is equal to anything from Symbolic Python. I import that as sim. So I'm gonna say sim first, and then I'm gonna call a function inside Symbolic Python, which is symbol, and then call it t. Okay, so by doing this here, I'm telling Python that I have a symbol or variable which I call t. All right. Then I'm gonna solve it. Solution equal to Symbolic Python have a function called solve, and I'm gonna just implement my equation, but I'm gonna write it as the quadratic equation. So this is gonna be let's see, 0.5 multiplied by the acceleration, which is a, multiplied by the time squared. In order to get squared, we have to do double asterisk. That's like a power, to the power 2, plus, then it's the initial velocity times the time, minus, and then it's the final position minus the initial position. Okay, so this is my equation I have up here from kinematics, just written down in Python structure. I'm gonna solve for the variable t. Okay. And then I want to print the solution, so print solution. And let's see what happens when you execute this here. Nothing. Let's see what happens here. Oh, there we go. It just took a little bit of time, huh? Okay. Oh, hang on a second. I think I made these numbers look different from what I had. I said up here it had an initial velocity of 50. That's too much. Initial velocity of 5. I want to keep it the same as I had earlier in my notes. So down here I'm gonna make it initial velocity of 5 meters per second. Let's solve it again. Okay, so these are the two solutions we have. Remember, this is a quadratic equation, right? But keep in mind that we are starting at t equals 0, and therefore as time goes on, the solution to our answer will be 7.32 seconds. You could have plugged that into the quadratic equation, you would get exactly 2 numbers. But here we let Symbolic Python solve it for us. And if you get the hang of this here, get used to it, you'll find out that might actually be a lot quicker sometimes. And you may be less inclined to actually make a mistake. So this is definitely one strength of Jupyter, that we can write a little script to actually solve the equations for us. It can solve derivatives, integrals, differential equations, much more complicated structures than this here. Let's take another example to illustrate some of the strength here. Let's say we want to make a plot. So we're going to import functions that we will need for plotting. Okay. There's something called matplotlib. I will talk more about that in a different video. But it's pretty much a library full of plotting routines or plotting functions. From matplotlib, import pyplot as plt. Don't worry about what it means. And import numerical Python as np. Okay, so that's what I do here. I want the plot to occur or appear inside my document, not as a separate window. So that's going to be matplotlib inline. Okay, you notice I keep looking on the computer because I don't remember these syntax myself. I keep looking them up and maybe do a little bit more copy and paste than I should. But the more I use them, the more I used to get them. I'm going to have our constants. In principle, I don't have to redefine them because already defined in the previous script. But for good programming habits, it's good to redefine them here again. Okay, then what we're going to do now is I'm going to create a list / array of values, because I want to plot this here. So I'm going to say, well, imagine we took data points at t equals 0, t equals 1, t equals 2, t equals 3, and so forth. Those are kind of data points. But that means we have to populate those data points. Okay. Of t, I'm going to call them x values here. So we are going to have x equals to np.a range. This is a function that will create a list of numbers. I'm going to go from 0 to, well, we know that after 50 meters, it will take about 7 seconds. So let's go out to 10 seconds. But I want this to be in step size of, let's say, 1 second. Or should we do half a second intervals? Okay. My y values, so now x corresponds actually to the time. My y values will be actually be my x position. Okay. So I'm going to go up here and I'm going to copy paste this one here. So maybe I should just call this here for t, not to confuse it. So where t is the x-axis, and then our x values, I'm going to do this here. Okay. Let's see, write this out here. Okay, so that is our quadratic equation, or the value for x, giving a starting position, and then the time values. Okay. Now I'm going to set up a plotting environment. First, I'm going to create a figure. It's not going to actually make the figure, but that's from a PyPlot. So I'm going to call plt dot figure. Okay, initializing that one. I'm going to make an axis environment. I'm going to make sure it fits inside my prescribed window. Actually just maximizing the size of it. And then I'm going to plot the functions. I'm going to have time on one axis, that's horizontal axis. I'm going to have x, my position, on the vertical axis. And then I can make some tricks where I want to have like a line connecting the data points. I also want to have symbols, like little round markers for each data point, and I'm gonna make it green. So these are keywords we can learn as we go along. I'm gonna make a title, set title. I'm gonna call this here problem 2. X set X label. I'm gonna make some labels on the axis. On the horizontal axis, that is time measured in seconds. X.set Y label. That's gonna be my position in meters. So that's the X position, right? Okay, so let's see if that will work. Let's hit Shift Enter and see what happens. It's working. Here we go. There it is. So that's our position in meters. And we can go after about 7 seconds. We are right around 50 meters, which is what our numerical solution did as well. So we can now create a plot showing the solution. So you can now compare to if you just did this in Word, for example, you have to use the probably quadratic equation solver. You plug in your numbers, you get a value out. But there's so much more information you can give here with a graph, for example. Let's say, go ahead and make some changes here. Let's say, for example, we are starting at the same position. But let's say we want to know if we go, let's say, 10 seconds back in time, where were we? Well, all we have to do is just extend this graph 10 seconds back. That means we take our time, and this list, we're going to now start at -10 to 10. And let's see what that does. Okay, that means after 10 seconds we were at a position that was, what is that, maybe 25 meters behind us of where we started from. Right? We can go even further back in time. And now we can also say at what time were we at x equals 0 as well. Now you can see we have two roots. We already knew from our solution up here, our two roots was 7 seconds and 27 seconds. So at 7 seconds, we will be at 50 meters, right? So that's out here. We will be at 50 meters again at about 27 seconds earlier. So this here is much more representative of, a much more in-depth representation of the problem. And this is the strength of using Jupyter. You will say, like, I don't know how to do these things here, but you recognize that we will do these things over and over and over. At a certain point, when we do this repetitive process, you'll become comfortable in actually using it. So I do suggest take these examples here and play around with them, change the numbers and see what happens. You can also say, instead of green, maybe we want to do red. Easy to do. You can say, okay, what is the effect of increase the step size in the array, for example? Well, now we only get data points every 1 second. We could get a data point every 5 seconds. Right? Now you can start seeing now it's getting more jagged because there's bigger spacing between our data points, and you just want to make a straight line between the data points. Okay. But really just show the strength of using Jupyter or a traditional text editor like Microsoft Word or anything like that. So we will do this here quite a bit in notes. You're not required to write the code. In the lecture notes, I provide the code. You can go in and modify and change it. You can copy paste into your homeworks if you want to. You're not required to use it for homework, but it is strongly encouraged.